So we're going to talk about inductors and inductance today. And this is our first step towards non-DC circuits. Okay. I'm not going to call them AC circuits just yet, because that typically implies that you have sinusoidal excitation, and we're not there just yet. So we're just saying it isn't necessarily a DC thing that we're going to be talking about. Okay. So the first thing that I want to bring up today is what an inductor is. Okay. So what is an inductor? Put simply, it is a two-terminal electrical component consisting of a coil of wire wrapped around a core material. Okay. So this class is not a material science class, nor is it a class that deals a lot with electromagnetic field theory. So I'm going to gloss over some things here when we talk our way through. That'll be covered in your later classes for those of you that go further into electrical engineering and all of this kind of stuff. But I'm going to start by drawing a couple of pictures. Okay. So the picture that I'm drawing here on the left is what's called a solenoidal inductor. And so what I'm trying to draw here, but my artistic talents are rather limited, is a cylindrical core around which we are going to wrap a section of wire. Okay. So I'm just going to wrap the wire around it some number of times. Like so. And this N right here is just the number of turns of our coil. Okay. So if this is part of some larger circuit, we might have some current I flowing through the coil. And I'm going to define the positive polarity of the voltage such that the current's flowing into the positive polarity terminal and our coil is set here to absorb power. Okay. So this is our solenoidal coil, and I'm going to add some stuff to this picture here in a moment. Before I do that, I want to introduce the other type of inductor that you might see very regularly. And this is what's called a toroidal coil. And so I have to draw circles, which I am even worse at than other things I'm trying to draw, so bear with me. Okay. So what we should see is something like this. So we have circle, and I'm going to attempt to draw another circle around it. Like so. So think about this as effectively a donut-like shape. Okay, that's what a toroid is. So I might wrap a wire around this as well. Okay. So if I start my coil here, like so. Let's say that I is flowing in here, and our voltage drop across our terminals will be like so. So this is our toroidal coil. Okay. So these inductors behave in a very particular way because of magnetic fields. Okay. So I want to just do a quick aside here to talk about the behavior of magnetic fields, and that's going to kind of help us understand what's going on a little bit. Okay. So let me just put a quick aside. So let's say that I had a section of wire like so, and it was carrying some DC current I. Okay. How many of you have had Physics 202 yet? A couple of you guys, right? So in Physics 202, you probably learned something called the right-hand rule. And applied to a simple straight wire like this, effectively, when our thumb points in the direction of current flow, our fingers wrap around and tell us the direction of the magnetic field. So we should see that our magnetic field lines are directed out of the board for regions of space above the wire, and they're directed into the board in regions of space below the wire. So I'm going to try to represent that. So things coming out of the board, think about these as like the head of an arrow sticking out through the board. And then below, I'm putting just the tail of the arrows. So our magnetic field lines form closed loops or rings around our current carrying wire. Anytime we have current flowing, we have some magnetic field, because the magnetic field is related to the motion of charges. Okay. So let's think about what would happen if I turned my long section of wire into a ring. Okay. So if our thumb is in the direction of current flow and it's circling around over and over and over again, what we're going to see is that our field lines should be directed down inside the ring and up outside the ring. And if our current was in the opposite direction, it would be up inside the ring and down outside the ring. Okay. Well, when we have a solenoidal coil, that's nothing more than effectively a stack of rings. So what we should see is along the axis of symmetry, effectively, we're just going to have magnetic field lines directed up like this, or down depending on the direction of the winding and the direction of the current flow, but we're just going to assume up for now because I don't want to get too bogged down in the details. And then as we as we move away from the axis of symmetry, what we'll see is that the field lines kind of bleed off and then wrap around in on each other. Like so. So something looking roughly like this. Okay. So whenever we have a bunch of magnetic field lines passing through a confined area, like the surface, the cross-sectional surface area of this coil, have what's called a magnetic flux, where that literally just means it's like the sum of all of the magnetic fields confined to that particular region of space. Okay. So wrapping our wire up into a coil tends to bunch a bunch of flux together inside the coil, and we see that it spreads out as we get outside of the coil region, okay? In our toroidal coil, this geometry actually causes all of the flux to be confined within the toroidal core itself. So we just have flux that's going to circulate around inside this thing. So I'm going to call these lines here magnetic flux. Same over here, like so. So if our current is a time-varying quantity, then our flux will also be a time-varying quantity, right? So as our current changes, our magnetic field strength changes. As our magnetic field strength changes, our magnetic flux changes, okay? So inductance is a measure of how a circuit element responds to a change in magnetic flux strength. So let's think about this a little bit, okay? So we know that any current carrying wire generates some amount of magnetic field, but when we coil things up, we tend to concentrate those flux lines. So any wire that's carrying current is going to exhibit some level of inductance because it is part of a closed current carrying path. But the more we confine that magnetic flux into one particular area causes the inductance of our element to increase. So we use coils like these to form regions that have high inductance. So they respond greatly to a changing magnetic field, effectively. So that's all an inductor is. So what is kind of interesting about these things is that if we confine our magnetic field lines to a particular region where things are real confined and tight, we actually form an energy storage system. So inductors are used as a form of temporary energy storage within a circuit. And we're going to talk about capacitors on next Monday. They are also a form of temporary energy storage. And it's a little bit easier to understand where the energy storage comes about for a capacitor than it is for the energy storage behavior of an inductor without just using a bunch of math to explain that there's going to be energy stored, okay? So for right now, you'll kind of just need to take it on faith that this is an energy storage element, but that is exactly what its role is in any given circuit, okay? So let's throw some math at things and see if we can't figure out what's going on, okay? So our magnetic flux which has a symbol of phi b, is equal to our inductance L multiplied by our current I. And so from this, we can say that our inductance L is simply the ratio of, let me be consistent about which, if I'm using capital phi or lowercase phi here, is the ratio of phi b to current I. So effectively, it's the ratio of the amount of flux we have to the amount of current that's creating that magnetic flux. Okay. So dimensionally, inductance is measured in henries. So 1 Henry, which has a symbol of H, is equal to 1 Weber per ampere, where Weber is the unit of magnetic flux. Now, I understand that most of you guys probably don't know what the hell a Weber is. So let's break it down a little bit further than this, okay? So a Weber is nothing more than a volt second. So a Henry is a volt second per amp, which is how I usually think of Henrys. But we know that a volt per amp is just an ohm. So we could also express Henrys as 1 ohm second. Okay. So we have lots of different ways to represent the unit of a Henry. Okay. So 98% of the time, I consider a Henry a volt second per amp, but every now and then it's a little bit easier to for me to think of it as an ohm second. I practically never think of it as a Weber per ampere unless I'm dealing with magnetic circuits, which are an entirely different class that you guys don't have to worry about. Okay. So I think we've gotten a reasonable-ish idea of what an inductor is and what inductance is. So what I want us to figure out now is what the relationship between the voltage drop across our coil is to the current that's flowing through it, okay? And that is governed by what's called Faraday's law of induction, okay? So Faraday's law of induction states Faraday's law of electromagnetic induction. So mathematically, this is just E is equal to negative times the derivative of the magnetic flux with respect to time, like so. Where that fancy looking E is the symbol for an electromotive force. So an electromotive force is a force per unit charge that pushes charge carriers around a circuit. What did I just describe? Voltage. Voltage is the work done per unit charge, moving charge from point A to point B. So a voltage is always an example of an electromotive force. So we could just as easily replace that E thing with voltage, okay? Now, we know that our magnetic flux, phi B, could simply be the product of our inductance L times our current I by rearranging that expression I have up above, right? We are going to make an assumption here that it's not always true, but it will be for this class, that our inductance is incapable of changing as a function of time. So our L value will be constant. So that means that I would have the derivative with respect to time of L times I of t, and I can pull that L outside of my derivative, leaving me with di by dt. Now, some of you may have noticed that my left-hand expression has a negative sign and my right-hand expression does not. Okay. That negative sign is taking into account what's called Lenz's law. And Lenz's law states effectively that nature hates a change in flux. Okay. So contextually, what this means is that our induced current or induced voltage will be made opposite to any change in flux that we observe. Okay. So just to provide you guys with some context about Lenz's law and all of this kind of stuff, and actually induced voltages and current, how many of you have ever unplugged something from the wall while it was, whatever device it was turned on? Probably a lot of us. Did you ever see sparks or anything when you did that? Yeah. Those sparks are a physical manifestation of Faraday's law of electromagnetic induction. So effectively, there was current flowing through that circuit. Okay. So there was some amount of flux flowing through its closed magnetic path. And when you abruptly unplug it, the flux doesn't want to change. So what happens is the air between the terminals of the receptacle actually becomes ionized, generating a plasma that allows current to continue flowing for a few milliseconds, microseconds, nanoseconds, depending on what the inductance is, to make sure that that flux gradually decays instead of abruptly decays, because as we'll find out here in a couple of minutes, that would literally cause an infinite voltage to appear, okay? So anytime you ever unplug something and you see sparks, that is literally Faraday's law of induction in action, trying to make sure the flux doesn't change abruptly. Okay. So we have our mathematical relationship. This is one of many. I'll come back to it in just a moment. One other thing that I want to give you guys just really quickly is representing inductances in a circuit. So effectively, I'm going to show you what the schematic diagram symbol is. So there's our schematic diagram symbol. It looks suspiciously like a spring. And it literally represents a coil of wire, because that's all an inductance is a coil of wire. Okay. So we would put some magnitude of inductance L. I'm going to define my positive polarity terminal, to be over here on the left. So this will be the voltage drop across my inductor. And then I'm going to define my current IL is flowing into the positive polarity terminal, because inductances should be, obey the practical sign convention like literally everything else in this class. So when current flows into the positive polarity terminal, our inductor is absorbing power. If we saw current flowing into the negative polarity terminal, our inductor would be supplying power. And for what it's worth, since an inductor is a form of temporary energy storage, it can actually supply energy to our circuits, okay? So we won't have the luxury of knowing it's always absorbing like we did for a resistor. Okay, so let's talk about circuit characteristics here. So a few minutes ago, we came up with the relationship that the voltage drop across an inductor is equal to L times the derivative of the inductor current with respect to time. This is our first of 4 equations that we are going to develop today. Okay. This one is particularly important, A, because it's a derivative, and since I hate integrals, this is the one that I prefer to use if at all possible. So that's why it's personally important to me. But there's a couple of other pieces of information that we can glean just by understanding this relationship, okay? So let me ask you guys what I hope is a fairly straightforward question. If the current flowing through my inductor is a constant, meaning that I have a DC circuit, what must the voltage drop across my inductor be? 0, because the derivative of a constant is 0. So that means that based on this mathematical relationship right here, which is nothing more than Faraday's law of electromagnetic induction, we can say that in a DC circuit, inductors behave like a short circuit. Okay. So mathematically, this makes sense because, like I said a moment ago, if the current doesn't change, the derivative is equal to 0, which means the voltage has to be equal to 0. Does this make sense from a physical standpoint? Well, I think so, because an inductor is nothing more than a coil of wire. And what do we know about wire? How have we been treating wires in this class? As if they have 0 resistance, which means they have 0 voltage drop over them. So this tracks with what we've learned previously as well, okay? So this is our first thing that we can glean from this particular relationship. Now let's look at something different, okay? So still using just this simple relationship. So let's say that I have the following current flowing through an inductor. And for the sake of argument, let's say that we're dealing with a 1 Henry inductor so that the math is pretty easy. So I'm just going to put here L is equal to 1 Henry. And my current is going to start at 0. Then it is going to linearly increase up to some value, stay at that value for some amount of time, and then linearly decrease back to 0 like so. So let's just throw some numbers here. So let's say that this is 5 amps. Here we have 0 seconds, 2 seconds, 4 seconds, and 6 seconds, like so. And what I want us to figure out is what the voltage drop across our inductor is going to look like over this interval. Okay. So for all time less than 0, we are assuming that our inductor current was a constant value of 0. So I believe that we could pretty easily infer then that the voltage drop across our inductor had to be 0 as well. Okay. Over the interval from 0 seconds to 2 seconds, now our current is changing. So we should observe some amount of voltage drop across the terminals of our inductor based on that mathematical relationship, right? Anytime our current changes, the voltage drop across our inductor will be non-zero. So I have an L value of 1 Henry. The derivative of our current with respect to time is nothing more than the slope of that line. So that would be 5 amps every 2 seconds. So that to me looks like a slope of 2.5. 2.5 amps per second times 1 volt second per ampere gives me a voltage of 2.5 volts. Just to look at the units here just really quickly, just so that we're all on the same page. So VL of T is going to be L, so that's 1 volt second per ampere multiplied by our slope, which was 5 amps every 2 seconds. So the seconds cancel, the amps cancel, and we're left with just voltage, so 2.5 volts. So from 0 to 2 seconds, we have a voltage of 2.5 volts. Okay. At t is equal to 2 seconds, or on the right-hand side of t is equal to 2 seconds, our current is now constant. So we should see that our voltage falls abruptly back down to 0. And it's going to stay 0 until we hit t is equal to 4 seconds. And then what's going to happen over the interval from 4 seconds to 6 seconds? It'll be negative 2.5 volts because our current is decreasing, and so the derivative gives us a negative value. Okay. So let me just put some things on here. So this represents 2.5 volts. This is negative 2.5 volts. Once again, we have 0 seconds, 2 seconds, 4 seconds, and 6 seconds, like so. Okay. So what would happen if my current changed over a smaller interval of time? So right now, it takes 2 seconds for it to go from 0 amps to 5 amps. But what if it only took 1 second? The voltage would double, right? So the shorter I make that time interval, the larger my voltage is going to be. So let's consider a case where my current is 0 until some point in time, which I'm just going to call T1. And then it instantaneously changes to some value, stays that value for a little bit, instantaneously falls back down to 0, and then stays at 0 like so. So let's just call this time T1, this time T2, and for what it's worth, this will be 10 amps, just to throw a number on it. Over here on the right, I'm going to plot what our voltage should be, and I would like some input from you guys. So here's T1, here's T2, here's VL of T. Okay. So from 0 to T1, we have a value of 0. What happens at exactly T is equal to T1? Our current changed from 0 amps to 10 amps in 0 time. What is our slope? Infinity, right? We have a fixed rise over an infinitesimal amount of time. So our slope looks like infinity. So what we would see is what would commonly be referred to as a delta function or an impulse function, having an infinite height at this particular point in time. Then our current is constant. And then at T2, we would have a negative impulse. Is this something that could ever physically be realized? Well, absolutely not, right? Those impulses represent an infinitely large voltage across the terminals of our inductor. So recalling from way back on the second or third day of class that a voltage is representative of a transfer of energy, that means that we are transferring an infinite amount of energy in an infinitesimal amount of time. Literally cannot happen. So the second thing that we can glean, I should have done that in blue for what it's worth so that we could see the difference between the signals. Let me do that real quick. Doesn't matter. So the second thing that we can glean from this derivative-based relationship is that the current flowing through an inductor cannot change abruptly. And what I mean by change abruptly is effectively our inductor current has to be a continuous function of time. We can't have a place where its derivative is infinity, because if we do, we're violating the laws of physics. So those are the two very important things to glean from this particular first voltage current relationship equation. Okay. That second statement, the current flowing through an inductor cannot change abruptly, we are going to use as kind of one of the fundamental building blocks or the fundamental truths of our circuit analysis when we get to transient analysis starting next Wednesday. Okay. So that statement right there is going to tell us a lot about what the expected behavior of an inductor is when we start having circuits where we allow things to change, which is all transient analysis is. Okay. So I'm putting a pin in that one because we're going to use it a whole heck of a lot next week, but for right now, it's just an abstract thing that we understand it can't do that. Okay, so let's come up with our second relationship. So if I start with this guy up here, and then I literally just rearrange things, right? So I'm starting with my equation. VL is equal to L di by dt. And so I'm just going to rearrange this. So I'm going to do something that all of the people that have a math minor are going to hate. I'm going to say that VL times dt is equal to L times dl. So I'm just multiplying both sides by dt. And now I'm going to integrate both sides. Actually, I'm going to divide both sides by L. Let me just do that as a separate step. So I'll have 1 over L times VL of t dt is equal to DIL. And integrating both sides then gives me IL of t is equal to the integral from negative infinity to positive infinity of 1 over L times the voltage drop across my inductor. I'm using that T prime dummy variable again, where that never indicates taking a derivative in this class. That is just a dummy variable for time. Okay. So this is one representation, and there's nothing particularly wrong with it, but there's another more commonly used expression for current as a function of voltage, okay? And so that more commonly used expression is this guy. So we'll have the same thing, 1 over L. Sorry, that shouldn't be infinity, that should be t, my bad. Will be the integral from 0 to t of VL of t prime dt prime plus IL. Damn it, I'm just losing my mind today. My apologies. So that 0, I've changed it to T naught, and I'll talk about what that means here in a moment. So effectively, what this T naught represents right here, and I apologize for being so scatterbrained today, this T naught right here just represents some point in time where our inductor current is a known quantity. So for those of you that have had Math 245, this is an initial condition on the system, okay? So This lets us no longer have to integrate from the beginning of time when the inductor was created to just some point in time where we knew what was going on to some later point in time that we are interested in, okay? I want to make a note here. This part right here is not inside the integral, okay? So it is literally just perform the integration and then add on some constant value at the end that represents what we know the inductor was doing, okay? So let's put this equation into practice because this is one of the ones that tends to give you guys a little bit of difficulty in implementing. So let me just find a quick example of this problem here. And if I can't find one that I like in all of these damn notes, I will just make something up. Here we go. So let's say that we have a 250 millihenry inductance, like so, where this is the voltage drop across the inductor, and this is the direction of our current flowing through the inductor. And the voltage drop across the inductor is given as a piecewise function. So we have 0 volts for t less than 0, and 5e to the negative 4t volts for t greater than or equal to 0. And we are also told that IL at 0 is 2 amps. Our goal is to find IL as a function of time. So the first thing that I want to ask you guys is related to what we talked about a moment ago, okay? So the inductor current cannot change abruptly. But this expression right here for the voltage drop across the inductor, it is 0 volts at the moment before t is equal to 0, and it's going to jump up to 5 volts at t is equal to 0. Is that okay? Yes, because it's an inductor voltage. There are no constraints on the behavior of inductor voltages, only inductor currents, okay? So the inductor current cannot change abruptly. The voltage can do whatever the hell it wants. So I just wanted to be clear about that. Okay, so realistically, this should just be a pretty straightforward application of this equation right here. I just want to sort through things to make sure we have an understanding of the units and how to apply it and all of that kind of good stuff, okay? So we would have IL is equal to 1 over L times the integral from t naught to t of VL of t prime dt prime. So that's going to look like 1 over 250 millihenries. So 250 millihenries is the same thing as 0.25 Henry. So I'm going to put 0.25 here just so that I'm dealing with base units. Okay. A Henry is a volt second per amp. So I've taken care of my 1 over L term. Now I'm going to integrate VL. So that is 5 volts times e to the minus 4t prime dt prime. My limits of integration are going to be from t naught. So what's t naught here? 0. So at t is equal to 0, we know some value. So that's what t naught is that 0. Okay. So we're going to be integrating from 0 to t. And then we are also going to, shit, I forgot the other thing here, so I'm going to sneak it in. My apologies. Again, I'm losing my damn mind today for whatever reason. And then we're going to add 2 amps to this thing. So let me just take some of this stuff outside. So I have 1 amp over 0.25 volt seconds. I'm going to pull that 5 volts out. How do I integrate e to the negative 4 t prime? So I don't know what all that U sub stuff is. Gross, gross, gross. So just for what it's worth, because we do, we're going to be working with exponential functions a whole hell of a lot here over the next several days. If I need to take the derivative of e to the at, that is a e to the at. If I need to integrate e to the at dt, that is 1 over a e to the at plus c. So to me, that means I'm going to pull down a factor of negative 1 over 4. So I haven't explicitly stated it here, and I do try to explicitly state things like this on the exams and all of that kind of stuff. But that 4 has units, okay? So the argument of the exponential function needs to be a dimensionless quantity, okay? So if t, or t prime, is time measured in seconds, then that 4 needs to have units of per second, okay? So it's what we would call a natural frequency of the system, and we'll talk more about that when we get into the transient analysis. But anytime you see anything multiplied by t in an exponential function, you should be assuming that the units of that are in per seconds in order to make the math work out correctly. Okay. And then we'll have e to the minus 4 t prime evaluated at t and 0, and then to this we'll add 2 amps. So let's look at how things are shaping out from the units, okay? So I've got a volt in my numerator and a volt in my denominator, so that seems okay. I have a second in my denominator and a per second in my denominator, so when those guys multiply each other, they're going to cancel each other out. And the only thing that survives out of that whole integration bit is just amps. And then I'm going to add that initial condition of amps as well, so that I'm only going to get amps as the resultant of this mathematical series of operations, okay? So simplifying things here a smidge, I have 5, actually negative 5 amps, and then I have 0.25 times 4, which is just 1, right? So all of this garbage out here is literally just negative 5 amps. Then I will have e to the negative 4t minus e to the 0, which is just 1, plus 2 amps. So this is going to look like, so negative 5 times negative 1 is positive 5 plus 2. So we will have 7 minus 5 e to the negative 4t amperes as our inductor current. Yes, sir. What about this 4 right here? 4 times 0.25 is 1. Yep. So anybody have any questions, comments, or concerns about how we applied this equation? I will tell you, particularly with the WebWorks and all of that kind of stuff, where you are expected, like you're given some units to aim for, it is going to be pretty critically important for you guys to be paying attention to the units throughout your calculations, because you're going to get some weird, funny stuff if you don't, okay? So you could largely not worry about the units too particularly much when we were doing all of that DC circuit analysis stuff, but when we're dealing with inductors, when we're dealing with the capacitors and stuff like that, the units are going to matter because of the complexity of the math that we're doing. So I would highly encourage you to pay attention to the units and use them throughout things. Don't just tack them on at the end and hope for the best. Okay. Okay. So let me scroll back up here. So this is equation 2. Okay. So we have, just to recap, our first equation is the voltage drop across the inductor as a function of the current flowing through the inductor. Our second equation is the current flowing through the inductor as a function of the voltage. So these are really just the same equation, just moved around and stuff. Now let's talk about power. Okay. So the power absorbed by an inductor is, what do you guys think it's going to be? I times V. Absolutely right. Because it's always I times V. So this can be just VL times IL. That L is looking a little C-like. And if I substitute in that first equation that we came up with, I could express this as L times our inductor current times the derivative of our inductor current. So realistically, the only thing I need to know to determine the power absorbed by an inductor is the inductor value itself and then the current flowing through it. That being said, 95% of the time, I wind up using the V times L relationship because that's winds up being easier based on the information that we have. Okay. So both of those are true, but I times V, that fundamental power relationship, is probably the one that's more useful. Okay. So there is equation 3. And our last equation that we're going to come up with, I'm assuming none of you guys have any questions about that power relationship because it's literally just I times V and then direct substitution. So the last one that we have to worry about is our energy relationship. So the energy absorbed by an inductor is, by definition, the integral from negative infinity to some point in time that we're interested in of our power. And again, this relationship is just from the second day of class, right? Power, excuse me, energy is the integral of power, or power is the derivative of energy, okay? So let's substitute some things in here. So we're going to have negative infinity to t of L times IL of t prime DIL of t prime over dt prime. And then I'll have another dt prime out here. And so again, all you math folks are going to hate this. To me, a silly peasant-brained engineer, I can cancel out those dt primes. And so now I have an integral with respect to current, which means I need to change my bounds on my integration, or change the limits on my integration, right? Because I'm no longer integrating with respect to time, I'm integrating with respect to current as a function of time. So that would simply look like the integral from IL at t is equal to negative infinity to IL at the time that I'm interested in. And now I'll have L IL of t, d IL of t. Just for what it's worth, the reason why I was able to get rid of that t prime dummy variable is because now t is no longer in the limits of my integral, so I can just treat time like real time and not have to use that dummy variable. Well, what do you guys think the inductor current at the beginning of time is? 0. Yay. So this thing right here is effectively just 0. So what's the integral of effectively x dx? 1/2 x squared. In this case, x is IL. So this is literally just going to come out to be 1/2 L times our inductor current squared. So this is the energy absorbed by an inductor, or the energy stored by said inductor. So we've got those 4 equations, okay? Excuse me. All right, so there's one last thing that I want to cover, and then I will stop harassing you guys about this gross math. Oh, actually, before I stop harassing you about this particular gross math, you are not provided an equation sheet for exam 2. So the expectation is that you will have to memorize. I would much prefer it if you actually learned them, these 4 equations, okay? Now, when we deal with capacitors on Monday, we will have a different set of 4 equations that are these equations, except that everywhere we have I, we replace it with V. Everywhere we have V, we replace it with I. And everywhere we have L, we replace it with C. Because inductors and capacitors are literally the electrical duals of each other. So they literally just swap the relationship for I and V and swap L and C, and you're good to go. So realistically, you're going to have 8 equations that you have to memorize, but it's really only 4. So just giving you guys a heads up of my expectations there. Okay, so the last thing that I wanted to talk about for today is combining inductances. So let's say that we have several inductances in series. So I've got a network that's part of some larger circuit. Here's some inductance L1, some inductance L2, all the way out to some inductance L sub n, like so. Excuse me. This is the total voltage drop across my network of inductors. And so I'm going to have a voltage V1 is the voltage drop across inductor L1. A voltage V2 is the voltage drop across inductor L2, and so on and so forth. And here is the current that's flowing through all of those inductors in series. So if I were to apply Kirchhoff's voltage law to this system, I would get V of t, my total voltage, is simply the sum of all of those individual inductor voltage drops. I can express all of those voltage drops in terms of my common current I using that first equation, right? So that's going to look like L1 times the derivative of I with respect to time plus L2 times the derivative of I with respect to time all the way out to L sub n times the derivative of I with respect to time. Excuse me, I can then lump all of those inductances together since I have a common factor of the derivative of I with respect to time. So this is going to be L1 plus L2 all the way out to L sub n di with respect to time, or LEQ di with respect to time, where LEQ is simply L1 plus L2 all the way out to L sub n, or the sum from I is equal to 1 to n of L sub I. In other words, inductances in series combine like resistances in series. So without making you guys suffer through another boring derivation, how do you think inductances in parallel are going to combine? Like resistances in parallel. All right, so I won't make you suffer through that math. It's very similar to this, except it's just using the integral relationship. And now I'm done with the material that I wanted to cover for today. So you've got an in-class assignment. If you have any questions about anything, please don't hesitate to ask. And then you wrap that up. Enjoy your Friday.